In most situations, when we encounter a vector quantity, it's going to be pointed at some sort of an angle, like this 30-meter vector that we see here in red. But our coordinate axes are usually going to be along the normal x and y direction, or using compass directions like this compass shows here, along the west and east and north and south. And so what we'll need to do is to take a vector like this 30-meter vector and break it into components. What that means is we want to imagine this 30 meters as if it were the hypotenuse of a triangle. And in fact, a lot of times we'll sketch in the rest of the triangle like this. And then we want to think about how that relates. So this is a right triangle. Well, this 30-meter vector is really pointing somewhat to the west. So this is my west component. And then somewhat to the north. And so I have a north component. And what I want to do is to find those two vectors. So I could call this one x and this one y. And then I could use my triangle trig understanding to find those. So for instance, x is the adjacent side to the angle of 36 degrees, and 30 meters is the hypotenuse. So the cosine of 36 degrees should equal my unknown x divided by 30 meters. Then if I multiply both sides of the equation by 30 meters, then I see that how to find the side is to take the hypotenuse, 30 meters, and multiply by the cosine. X comes out to be 24.3, and that would have the same units as the original vector that I was given, so 24.3 meters, but based on my picture I can see that that was pointing to the west. So I would label this component to the west. My other component of y, I could set up something similar, but now using the sine function. So sine of 36 is equal to y over 30 meters. Again, multiplying both sides by 30 meters, and 30 times the sine of 36 is 17.6 meters. And then that vector pointed to the north. And then I'd be ready to usually go to a second step in a problem. My vector down below should be in newtons. I apologize for that. Let me fix that really quick here. So this is 48 newtons. And our 48 Newton vector, it means there's a force that's pulling sort of down and to the right. Now, it might be that I use compass directions, but not always. So I'm going to use more of just kind of descriptions, up, down, left, and right for this one. So in this case, my angle that was given is the 28 degrees here. Okay, if I want to find the components, again, I want to imagine a triangle where this is the hypotenuse. And so I have one side here and one side here. There's my right triangle. And so this side now is my y direction, but I'm not just going to call it y because it's not a distance. I might get confused by that. It is a force, but it's the y component of the force. So I'm going to call that F sub y. And then on the other side, I have a similar idea. This vector here is pointing, or component vector, is pointing to the right, whereas this one was pointing down. This one is in the x direction, so I'll call it F sub x as my component. So let's find F sub x. That is opposite my angle of 28 degrees. So I would say that the sine of 28 degrees is equal to F sub x divided by my hypotenuse, 48 newtons. Again, multiply both sides by 48. And, notice this pattern. When we're finding these components, we often are going to be taking the hypotenuse times the sine, or the hypotenuse times the cosine. So if you start to notice that pattern, go ahead and take the shortcut and just sort of notice it. This is telling me that my F sub x has a value of 22.5 newtons. And again, if I look back at my picture, that was pointing to the right. So I'll just label it to the right. And then my f sub y is going to be pointing down. That is going to involve the cosine. With components, you're usually going to be using sine for one and cosine for the other. It's the usual way of setting it up. Again, I'm going to multiply both sides by 48. 48 times the cosine of 28 is 42.4. And again, from my picture, I can see that that is pointing down. It's really easy with these sorts of questions to mix up the two directions. So when you look at your diagram, if this angle here is 28 degrees, I expect that this side over here is the shorter side. So I'm going to expect that my f sub x is a smaller number. Those are things you can do to sort of check your work. All right, so this question asks us to find the resultant displacement. What that means is it's asking us to sort of find the quick route, as if you did these two displacements, instead of doing them separately, you just went directly from the beginning to the end. So what we have here is we have a car traveling 4.8 kilometers to the west and 8.2 kilometers to south. So I can kind of imagine it's going, sort of southwest. It's sort of going in this general direction. So I'm going to set up my diagram here. So this is my 4.8 kilometers to the west. And then from the end of that arrow, I'm going to head south. So I'm going to make my vector a little bit longer because it should be representing 8.2 kilometers instead of 4.8, so it should be longer. And then the answer that I'm trying to find is the resultant. And the resultant would be this right here. This would be if I just took the shortcut, if I just went from the very beginning to the very end, all in one straight shot. So that's my resultant. So how do we do that? Well, first of all, the resultant is a vector. It has a size to it, magnitude, and it has a direction. So I need to make sure that I find both of those things as I'm working through the problem. The magnitude is just how far am I actually going to be traveling. And that I can find using the Pythagorean theorem. So r squared would equal 4.8 squared plus 8.2 squared. So r would be the square root of all that. So 4.8 kilometers squared added to 8.2 kilometers squared. And I go through and do all of that, and I come up with 9.5. And since both of those are measured in kilometers, they have to be the same unit, then this answer also comes out to be in kilometers. The direction, I've got to be pretty specific about it. I can't just say southwest, it's sort of in that quadrant, the southwest quadrant. I need to describe how far south of west or how far west of south. So I'd go back to the beginning again, and this time, instead of looking at how far, I'm looking at what angle I'm moving in. So that's going to be my theta right here. So notice how that theta is with respect to the west direction. So when I describe this, this is going to be an angle that is south of west. All right, so what I know with respect to this angle, I actually know all the sides, but I'm going to go back and use just the original information. The 8.2 kilometers is the opposite, and the 4.8 is the adjacent. So that means my angle should be the inverse tangent of the opposite, 8.2, divided by the 4.8. I put the units in there just to make sure that I've got everything in the right units. If maybe I'd been given miles for one direction and kilometers for the other, I'd have to convert something. These units should cancel out before I use that inverse tangent. Make sure your calculator is in degree mode. And at this point, I'll take a look here. It looks like it's about 59.7 degrees. All right, so now I need to make sure I give a good answer that includes everything here, because that's not actually enough to just say 59.7 degrees. I need to give a description with that as well. All right, so we've got 9.5 kilometers, that's the magnitude, at 59.7 degrees, And again, my reference line is west, and I'm south of that. So this is south of west. Now, sometimes before you can do those sorts of things, you have to first combine vectors together. Like, for instance, I may have some sort of a box that's getting pulled by a whole bunch of people, and maybe somebody is pulling it to the right, maybe somebody is pulling it to the left, just make up some numbers here, and maybe somebody is pulling it in this downward direction based on my picture here. So let's say this is 8. Okay, so what I would first do is I would first combine together the things that I can combine together, the things that are pointing along the same line. So that would be everything along this x direction. I have 10 newtons forward, 4 newtons backwards. So I could redraw this picture that it's the same thing as having 6 newtons this way and 8 newtons this way. Okay, so that's really sort of what's happening to the box. But this is not a good way to draw a diagram using with vector math, because I've started all of my vectors at the same point. So what I'm going to do is I'm going to redraw this one more time, and this time I'm going to put my 6 newtons here, and then from the tail of that vector I'm going to draw my 8 newtons, and then what I'm trying to find would be this vector right here. This would be my net force vector that I'm trying to find. So if you come across these sorts of situations, if there's more than 2 vectors, first try to figure out what's the total amount that's in the x direction, what's the total amount in the y direction. You can draw this sort of a diagram if you need to, but again, really make sure that when you're adding vectors together, you use the head to tail method, where you draw one of the vectors, and then right from the end of that you start your next vector. Otherwise the direction will not come out correctly.